APL. All right, so let's talk about velocity. And kind of the reason that I wore my JPL shirt today, which stands for Jet Propulsion Lab, is Jet Propulsion Lab basically builds all the cool stuff for NASA. Okay, so one of my former students, Michael Staub, works for Jet Propulsion Lab, and if you remember, middle of September of last year, there was the Cassini mission, which is this probe that was orbiting around Saturn. And he was like the flight director for it, and he came out there and he says, "Hey, come out here. I'll show you, give you the inside tour of JPL." And it's like, score, okay. And so when you look at the complexities of trying to keep track of a probe that's orbiting Saturn, so let me kind of give you some perspective. So, not to scale. Here's the Sun. Here's the Earth. Here's Saturn, and the rings of Saturn. Okay, so let's say, all right, hey, we want to keep track of the velocity of this Cassini mission, the probe. Where is it at? Okay. Number one, you have such vast differences, like the time delays in the radio signals might be like 3 or 4 hours easily on a time delay from the time that it sends this signal to it. So if you look at the complexity, so this is looking down on top of our solar system. Number one, the Earth itself is spinning on its axis. Okay, so we're moving. The Earth itself is moving around the Sun. Now, the Earth doesn't move at a constant velocity, and you'll see this later. We're traveling in a slightly elliptical orbit. So we're either spend half of our orbit slowing down or the other half speeding up, because we're trading potential energy for kinetic energy. It isn't like we notice it's like, oh, now we're starting to speed up. Whoa, okay. That isn't. If you feel that, it isn't because of the Earth moving. There's something else involved. And so the Earth itself is moving. Now, if you think about it, how many days does it take for our rock to go around our sun? 365 days. How many degrees are there in a circle? 360. So each day we move about a degree around in that orbit around our star. Okay? So we're going around like this. So we're on a spinning rock that's moving around a sun. Now, out here you've got Saturn. Saturn itself is moving. Okay? So you've got a moving target there. So you've got this Cassini spacecraft that's orbiting around, and you're trying to keep track of where it is and how fast it's going. Well, within this room, it's pretty simple. Say, okay, we go out into the hallway, right? We have Shively run. Okay, all right, cool. Here's the distance. Our points are stationary. We can go start, stop, right? We've got the timing twins, right? Okay, boom, boom, here we go. We measure that. Simple. Home run deal. There are no fixed points out here. Okay, there's nothing fixed. You have the distant stars, the constellations, those are fixed, but those are a little bit tough to measure off of. So it's pretty cool how they do it. So if you've ever been on the street and heard like a siren go by, an ambulance, a train, something like that, it's what's known as the Doppler Effect. You go, okay, it changes pitch when it goes by, whether you're approaching or whether it's after receding. The same thing is true what happens with this Cassini mission. So it's continuously sending radio signals to the Earth. And so basically, if the probe is going towards the Earth, then when we get those signals, the signals become a little bit more compressed because of the fact that it's moving in the direction that it's sending the signals. If it's going away from it, then that the signal gets stretched out a little bit because it's going away from the source. Now, to further complicate things, it isn't like the Earth itself is stationary. So if your antenna that's receiving that signal is spinning on this side of the Earth, then it's going towards the signals that you're getting from the Cassini probe. If you're on this side, after you've gone past it, then you're receiving those signals that are going away from that. And so you have to compensate for all of that mathematically. And the Earth itself is moving in this orbit. So when we talk about velocities, what we're going to talk about is relatively simple. Hey, we have fixed points that aren't moving. But when you try and navigate in space, where you don't have any fixed points, it becomes exponentially more difficult. So if you've ever seen the movie Apollo 13, most of you have seen that? Okay? Right? If you notice, when you look in windows, there's like etches that are marks that are etched in the windows. because what they would do is they would navigate, they had the ability to navigate with the stars, because the stars are fixed points. So like they would know when they're going to a particular point in that path towards the moon, which stars should be visible at particular points along the way. And so they would use these grids as basically a reference to say, okay, you know, is this particular star visible when it should be? And if it is, we know we're on course. If it's not, then we know that we're off course. And so that's what they would do as like a backup to the computer systems that we're trying to get them to the moon. And to kind of give you some perspective, even on the Apollo mission, to try and get in orbit around the moon. So here's the scale. So imagine you're standing on one end of a football field. The moon is an apple at the other end zone, okay? So that's on kind of a scale, that's what it is. So you're here, the moon is an apple at the other end. So to get that Apollo mission to put the spacecraft into orbit, you have to nick, not hit, you don't have to hit the apple, you have to nick the skin on the apple that's 100 yards away. That's the size of the target that they had to hit on that kind of scale. Because if they're too far out, you won't get caught in the moon's gravitational field. If you're too close, you crash into the moon, that's bad too. So that would tend to give you some type of scale of what you're trying to navigate. And even then, okay, here's the Earth, here's the moon, guess what? The moon's continuously moving, the Earth is continuously moving. So you had to compensate for that whole moving system, trying to keep track of that velocity. Okay, so let's talk about what we can deal with. So we're going to start with a relatively simple example, and we're going to build that into something much more complex. But if I can get you to understand the simple, the complex becomes much easier to understand. So we're going to look at a road trip involving the great state of Kansas. So here's Kansas, okay, and here's Wichita, America, here's Kansas City, and then here's Winfield, okay? Now, so let me kind of lay out the rules. Rule number one is that we're only going to deal with one dimension at a time, for now. Eventually we'll deal with 2 dimensions, eventually we're going to deal with circles and ellipses and all this other stuff. So, for now, imagine that I'm up here and there's like this huge number line. So the only thing we can do is talk about me going in one direction and then coming back. Walking around in circles, we'll deal with that later, okay? So imagine that you're only dealing with one plane of motion at a time. So imagine Wichita, Kansas City, Winfield are all on one big number line. So here's the grand idea. There's more to the story, but we're going to go from Wichita to Kansas City back to Wichita, Wichita to Winfield, Winfield back to Wichita, and that's where we're going to end up. So, what's the first thing that we need to pick?
Starting point?
Starting point, the reference point. So you have 3 options to begin with. You can choose Wichita, Kansas City, or Winfield, but you could also pick St. Petersburg, Russia, you could pick Paris, London, you could pick Dodge City, Kansas. Why, I don't know, but you could. Okay? So, which one do you want to pick? Wichita. Why?
Because we're here. That's where we start the trip.
So is Kansas City and Winfield.
But it's where you
It
start
isn't
the
like
trip.
Kansas City and Winfield are moving.
It's in the middle.
It's where you
It's in the
start.
middle?
It's where you start the
It's where we
trip.
start. Now, one of the things, and that we're going to establish some golden rules. One of the golden rules is not that the reference point has to be where you start. Okay? Your starting point does not have to be the reference point. A lot of times it is. Okay? Because a lot of times that makes life simpler. But it does not have to be your reference point. Okay, so all right, we're cool. We're going to make Wichita the reference point. Now, I'm going to work in kilometers because we're going to be dealing with such large distances. Now, here's the next question. Do you want Kansas City on this side to be positive or negative positions? Mary?
Positive,
Positive. Why?
because it's above us.
Okay, all right. That's cool. Or it's to the right. Okay, either one. So I'm going to make Kansas City have a position of positive 300 kilometers. Okay? Now, there is no hard and fast rule that says, oh, that has to be positive. If you want to make it negative, you can make it negative. Okay? There are no set rules. But once you establish a system, you have to use it consistently. Okay? You can't deviate from the theme. So if you want to make this positive because it's to the right and that's how you're thinking of number lines, hey, great, fantastic, okay, beautiful. You could have made this negative. It still would have worked. So that means Winfield's position is going to be negative 100 kilometers. Okay, so here's our framework. We're going from Wichita, which is 0. Here's a positive position up in Kansas City. Winfield's got a negative 100. But again, we could have easily made Winfield 0, Wichita 100, Kansas City 400. We could have made Wichita or Kansas City 0, negative 300, negative 400. Doesn't make any difference. It's just however you choose your system. But once you choose your system, you can't change it. Okay? So as they say, you know, Indiana Jones in The Last Crusade, choose wisely. Okay? Choose wisely. All right. So we got this. So I like charts. So we're going to set up a chart. And fill in some information. So we got the trip, position initial, position final, displacement, time, and velocity. Okay. So the first trip is Wichita to Kansas City. Okay. So, and initially this is going to be very simple, but it's going to become more complex. Okay. So what's my initial position? Wichita, because that's where we're starting, right? And we said, okay, we're going to make that the same. Okay, that's 0. Final position? 300. Cool. 300 kilometers. Now, let's talk about displacement. And you're going to see the difference between distance and displacement. Displacement is a vector quantity. So if something's a vector quantity, it has two things. What does it have? Direction and magnitude. Okay? Now, how you calculate displacement, is always going to be position final minus position initial, P minus P naught. There is no variation on this theme, okay? None, 0, zip. You will never see this as P naught minus P. Always, always, always P minus P naught, okay? Always. Don't overthink this, always. So, if that's the case, what's my displacement on the trip from Wichita to Kansas City?
300.
300, right? So if I take 300 minus 0, I get 300 kilometers. Let's say that that took 3 hours to make the math easy. Now, when you talk velocity, velocity is displacement divided by time, which in this case is going to be 300 kilometers divided by 3 hours. I get 100 kilometers per hour. Okay, cool, right? You're going, yeah, Burkamp, I got this. Physics is easy, man. 300 minus 0 divided by 3. I got this. And then we can come over here because we said it was vector quantities. And my board can draw cool arrows. So I can come in and say, okay, here's an arrow. And I could let that represent my displacement, right? Because it's a vector quantity. So the length of the arrow shows how far I've gone. I went from Wichita to Kansas City. And it points in this direction. Okay, that's cool. All right. So, okay, that's how far I went and in what direction. And then I can come here and say, okay, well, I got velocity vectors too. Okay, all right. So I can come in here, draw my velocity vector. And we'll label that as a velocity vector, and it shows this is the direction that we're going. Now, what if you go, Mr. Burkamp, you know, I'm kind of down on the money, I need to get to Kansas City, car's broke down, but I got a horse. Okay, all right. So you throw a saddle on trigger and off you go. So if you were to ride a horse to Kansas City, would that change your displacement vector? Why not?
Because you're going to the same.
So going to Kansas City, right? Would it alter your velocity vector?
Yeah.
So what's going to change about your velocity vector? It's going to be much smaller, right? Okay. So if you draw your velocity vector for trigger, okay, you get something like that. Okay? There's trigger's velocity vector. You'll get there. It's going to take a while. But then you go, hey, Dad, you know, mind if I fire up the corporate jet? Dad goes, yeah, we're not using it. Go ahead. Now, you fly in the corporate jet. What's going to happen to your velocity vector? It's going to be huge, right? But in all three cases, you have the same displacement. You're just changing how long it takes for you to get there. Now, at this point, here's what you all are trying to do. Human beings have evolved to notice patterns, okay? And we're very good at it. Because observing patterns has allowed us to be successful as a civilization. Maybe it's tracking the migration of zebras across the African plains, or when to plant and when to harvest, or how to navigate, any number of things. This is what we do. We watch for trends. And this is what you all are trying to do. You all are trying to make observations that go, oh, right, maybe I can follow a trend here. So here's what you all are trying to think. You're trying to sit here and think, huh, if I'm going away from the reference point, I have positive velocity. Okay? And in this case, this is true. But here's what you will see. I want you to get out of your minds right now that positive velocity means that you're going away from the reference point all the time. It can happen, but it is not an absolute. I want you to get out of your minds right now that positive velocity means you're going forward. It doesn't, okay? Negative velocity does not mean you're going backwards. It doesn't, okay? Doesn't. So right away, I want to get this out of your minds right now before that seed even has a chance to take root, okay? Pull it out, okay? Positive velocity does not mean you're always going away from the reference point. It could, but not always, okay? Now, you get to Kansas City, right? And you look on your phone, or it's a smoke signal, I don't care, somehow or another, you receive information that Bubba's parents are out of town. And Bubba has great parties when his parents are out of town. So you go, dude, we got to get back home to Wichita because Bubba's parents are out of town. And everybody's going to be there. Okay, so now we're going to go from Kansas City back to Wichita. Okay, cool. So here's what we've got. So we've done our time, right? And now we're going to go from Kansas City back to Wichita, right? Okay? So, great. What's my initial position?
300. If the initial point of reference is still Wichita.
Yeah, once you set the parameters, you can't change it. Okay? So what's my initial position going from Kansas City back to Wichita?
300.
300. What's my final position? Now, what's my displacement? Why is it negative? It's always P minus P naught. So this is going to be 0 minus 300. It's going to give me a negative 300 kilometers. Now, you all know this drill by now. What are you all going to do wrong here? If I could predict what you all are going to mess up, what are you going to do in this calculation?
We're going to make it positive because you can't have negative distance.
Yeah, you're going to end up with 300. You're going to go, oh, 300 and 0. Oh, my displacement is 300. Okay? Promise you, that's what you're going to do wrong. Okay? Why is that a train wreck? Because it's wrong. Because you don't pay attention that it's final minus initial. You see two numbers and you go, oh, it's 300. Wow, whoa, what's Burkamp standing up there ranting and raving about? Okay? It's negative 300. Now, let's say that took 3 hours. So what's my velocity?
Negative 100.
Negative 100. Now, this leads us to one of the golden rules. Okay? One of the absolute golden rules. Did you change direction in Kansas City? Matt, did I change direction in Kansas City? Yes. Did my velocity change sign?
Yeah.
Yeah. Because I have positive velocity, then I've got negative velocity. So here is golden rule. So here is golden rule number 1. There's no exceptions to this whatsoever. An object changes direction the velocity changes sign. Okay? No matter how complex the motion is, I don't care if it's the Cassini spacecraft orbiting Saturn, if it's Gary the golf ball thrown up in the air, it's you driving home. I don't care. Whenever something changes direction, the velocity has to change sign. Okay? No exceptions. Now, don't throw circles into this. Okay? We'll deal with that later. But in a simpler linear motion, here's the deal. So if I take the yonder golf ball and I throw it up in the air, and oddly enough it comes back, what do you know about the sign of the velocity? Changes, right? Okay, right. So here's the million-dollar question. Vonda, do you want up to be positive or do you want up to be negative?
Positive.
Positive. Okay, why?
I don't know. I used to.
You like it? Okay. It's going up, it's a positive thing, right? Okay. So, Olivia, did it change direction?
Yes.
So what had to happen to the velocity?
The sign changes.
Change the sign. So your lab mate beside you says she wants up to be positive. So I have positive velocity on the way up, so I have to have velocity on the way down. Now if she had said, I want negative to be up, then it would have on the way down. Okay, that's it. Right, that's it. Now there's a whole bunch of different ways you can represent velocity. One of the techniques we use a lot is a series of velocity vectors. So when I ask you to draw motion diagrams, and I will ask you to draw a lot of motion diagrams because it's just a cool way of representing what's going to happen. So here's Gary the golf ball, and we're going to launch Gary up with some velocity that I'm just going to call v1. So here's my initial velocity. Because velocity is a vector quantity, I can represent it with an arrow pointing up that says, hey, this is the direction that we're going. And then the magnitude is shown by the length of the arrow. Okay? If I shot Gary out of like a cannon, this would be much bigger. Okay? But I just kind of gave Gary a nice toss and said, okay, yeah, here we go. Now, so this is right as it leaves my hand. This is right as it leaves my hand. Now, as this goes up, there are three things that could happen to this velocity vector at some point in time later. What's one thing that could happen to that velocity vector after it leaves my hand?
Increase, decrease, stay the same.
Max?
Increase, decrease, or stay the same.
Huh?
I don't know. It's three things.
Three things.
Yeah.
You got to one. There's three things. Well, on the way up, what's it doing? Slow it down. So how do you think I could show a velocity vector that represents an object that's slowing down? So when I draw this second vector, what do you think I'm going to do? Draw it bigger, smaller, or the same size? Smaller. Smaller. So I'm going to draw V2, okay, something like this. Is the ball still going up?
Yes.
Yes, it's still going up, but it's smaller because it is slowing down. Same reason, right? Now, the other thing that could happen is you could draw this velocity vector bigger, which means that after it leaves my hand, it's actually speeding up and it's going faster, which would be cool to watch. Okay? It's like you throw it up in the air, it goes up and it goes faster and faster and faster. Probably not going to happen, but it would be cool. So, another option is that when you look at the next segment, the velocity vector could get bigger. So it could get smaller, it could get bigger, or
Could stay the same.
it could stay the same. Okay? Because Mother Nature is a lazy prima donna. And Mother Nature would prefer for this velocity vector stay the exact same size, because Mother Nature is going, oh, come on, you're killing me. Okay? You already gave me one velocity vector, don't make me change it. And it's like, oh, and gravity's going, sorry, Mother Nature, I kind of get the vote. Mother Nature's going, oh, seriously? Okay. So, it's going to get smaller. Now, if eventually, if I were to draw a third vector, I would draw that even smaller. Okay? So I start off, I'm going up, but I'm slowing down as I go up. Go with this. Okay. Now, it's going to start to fall. Right? So then what could I do?
Draw like a arrow. I'd say like just a straight line. Just because it stops at one point in the air.
It's an instantaneous point in time.
Right.
But let's not worry about the stop for now.
Okay.
We'll deal with the stop later.
Okay, so then just a small arrow
Pointing,
down.
we'll even change color for dramatic effect. Okay? So this would be, now I'm going to call this V1 because that's the trip down. So then, what am I going to do? What are those vectors going to do? Get bigger, and they're still going to point down. Oh, okay, right. Here's like V2, here's V3. Okay? So, using these vectors, I can look at this and go, oh, the ball is going up, and it's slowing down. It changes direction, it speeds back up in the opposite direction. So I can say that in written form, or I can just say, look at the vectors. What do the vectors do? And that's going to tell you what's going to happen. Got this? Now, what we've talked about is displacement and velocity. Those are vector quantities. Now we need to talk about the scalar equivalence. So here's the classic example. Displacement is a vector quantity, so I use an arrow. But if I said, okay, for example, Libretto, roughly how far from school do you live? Half mile, okay? So, if he just tells me he lives a half mile away, that's just a distance, okay? I don't know which direction he lives. I just know that he lives a half mile away. So, distance is a scalar quantity. So if you look at this situation, if I said, hey, how far is it from Kansas City to Wichita? And if all I'm asking for is distance, you would say, oh, it's 300 kilometers up, 300 kilometers back down, okay? So if it's just a number, distance, you don't have to make it negative, okay? So if Libretto says, hey, you know, I'm a half a mile from school, okay, I don't know which direction, but I have a vague idea of where he's going to live. Now, if you say you live a half mile, which direction? East. Now, if he says he lives a half mile east, now that becomes a vector quantity. Because not only do I know how far away he lives, I know in which direction that he lives. See the difference? Now, how do you all keep track of how fast you're going, assuming that you do? Hopefully you do. How do you keep, what do you use to keep track of how fast you're going in your car?
Speedometer.
Speedometer. Okay? Now, speed is a scalar quantity. So if I said, roughly, great, on average, how fast are you going when you drive to school? Average. 42. Now, if Grape just says, hey, I drive 42 miles per hour to school on average, okay? All right. Does that tell me which direction that he lives? No. All I know is how fast he's going, okay? He could be parachuting in from a helicopter, okay? Be cool, right? Don't get me wrong, style points on that deal, okay? He could be driving south, he could be driving north, east, southwest, I don't know, okay? All I know is that on average, he's going 42 miles an hour. So your speedometer is just that. It just tells you how fast you're going. It doesn't tell you the direction in which you're going, okay? Because that's the fundamental difference. Now, if you have a speedometer that also tells you which direction that you're going, this would sound odd because it's a marketing nightmare, because then it wouldn't be a speedometer, it would be like a velocimeter, okay? Because it would tell you how fast you're going and in which direction. But that would be tough to say. It's like, oh, I broke my velocimeter. Okay, velocimeter sounds like some weird, like fast-running dinosaur that they discovered. Like, okay, the T-Rex kind of thing. Okay, velocimeter. I'm being attacked by it. It has magnitude and direction. It's right on me. So we don't call it a velocimeter. We call it a speedometer because it only tells you how fast you're going. It doesn't tell you the direction that you're going, okay? So if you were to look at speed, okay, your speed would be the same in both directions because you're going 100 kilometers per hour, okay? But you don't know which direction. Now, great, which direction do you drive when you get to school?
To get to school?
Yeah.
I drive west.
West, okay? He drives west, so which tells me he lives somewhere east of Mays High School, okay? So now if he says, hey, I drive west at 42 miles an hour, now I know which direction he's coming from. Because now he's indicated two things. So it would be like, okay, hey, you want to meet for lunch, okay? We want to meet for lunch. And Hunter says, hey, let's meet for lunch at 12:30. Okay. Now, if all I know is he wants to meet for lunch at 12:30, does that give me enough information to meet Hunter for lunch? Why not? I don't know where. Okay? Agave, Sonic, where are we meeting at? Okay? Paris, I don't know. Okay? Kind of cool. Actually, I don't like Paris. Actually, it wouldn't be bad if it wasn't full of French people. Oh, no. Oh, believe me. Oh, I could go off for hours on, no. Okay. Really not the point. So, but if he says, hey, let's meet at 12:30 at Taco Bell, hey, all right, hey, I can make the run for the board, right? I can meet him at 12:30 because now I have enough information. So the same thing is true of scalar quantities. Scalar quantities are just numbers, but sometimes that's all we need. Hey, what's the mass? 1 kilogram. It doesn't make any sense for me to say, oh, it's a mass of 1 kilogram north. No, okay? It's just 1 kilogram. That's all I really need to know. Okay, shut that down. Okay, are we going? Okay. Now, by the way, and today, showing off the guns or what?
Yeah.
Okay.
Send that guns out.
Turn it into.
No.
Show me those skinny arms.
It's not going to be a gun show. No.
Let's see it, Eli.
No.
Let's see him.
Hunter in weights class is flexing nonstop. He's rolling up.
Who is?
Hunter.
Hunter?
Yeah. In the mirror.
Hunter's
They're
in
doing
weights.
workouts.
Hunter, you got a thread hanging from that sleeve, man. I don't see Hunter as being standing there.
Please tell me you got that on
flexing
tape.
kind of guy.
I did, yeah. We're filming.
I just don't see Hunter being that kind of
Oh,
guy.
he is. He is.
Is this true, Hunter?
Not exactly, but I mean, I don't stand in front of the mirror, I just flex it in.
Make it better.
It doesn't. It really does not help your case.
Okay.
He's worse than this.
All right. Okay.
You want to
So here, today is what, and this will only happen like 3 or 4 times in this entire class. Today is what we call good news, bad news day. Okay? So the bad news is I'm going to talk like the entire time. Like I said, this only happens 3 or 4 times. The good news is you don't have any homework. Okay? So that's your trade-off.
Now I'm buying 2
Okay?
cups.
That's your trade-off.
He said, now I'm buying 2 cups.
Okay. He's in for 2 on that one. Okay. All right. And they also make great Christmas presents.
They really do.
Eli, I'll get
Oh, and
you
the
one.
shopping bags. I think.
Yeah.
Where you get the shopping bag and you put the thing in it with the sticker.
Oh, there you go.
Save the planet.
Hey, grandparents.
Bird Camp Save the Planet gift bag.
Yeah, you're done. You have it. It's just how many are you going to buy? Okay. So, here's the drill. So now, let's go back to the trip from Kansas City back to Wichita. Okay, so we can draw these cool arrows again. Whoa. Theoretically. There we go. Right? So there's my displacement vector. My velocity vector is going to point this way. Hey, we're going along. Now, at this point, and I'm not passing judgment, I'm just telling the story. For some reason, your car is completely filled with smoke. Maybe there's an electrical fire. I don't know. No projections on the source of the smoke. Okay? All I know is that the car is filled with smoke. So much so that when you completely pass Wichita, I mean, you don't even see any of the signs. And then when the smoke clears, you realize you're in Winfield. At this point, you're going, dude, okay, we are in Winfield and we completely passed Wichita.
We're missing Bubba's party, dude.
Yeah, that's
We're bringing the party to Bubba's. Oh, that's so
Sounds like a Harold and Kumar movie.
okay. Funny things happen on the way to Winfield. Okay, so here's the drill. So we're going to go from the thriving metropolis of Wichita, Kansas, to Winfield, Kansas. Okay? So now we're just going to look at this trip, right? We're just going to look at this trip. So, Nick, we're going from Wichita to Winfield. What's my initial position?
100. No.
I'm going, starting here, going to Winfield.
Oh,
What's-
0.
0. What's my final position going to be?
Negative 100. Okay.
Negative 100. Oh, okay, cool, right? So my position initial is 0 kilometers. My final position is negative 100 kilometers. Bree, what's my displacement?
Negative 100 kilometers.
Why?
Because you take the negative 100 minus 0.
Beautiful, okay? I go back to my displacement, I get negative 100 kilometers. Now, here's the deal. Did I go past the reference point? Yes. I went, now I'm going away from the reference point. So if you look at what's happening, at this point, I'm going down here like this. Now I'm going away from the reference point. I'm going away from the reference point. So why didn't my velocity vector change sign now that I'm going away from the reference point?
You didn't change direction.
I didn't change direction. Okay? So that's why I said I wanted you to get out of your minds the idea that positive velocity meant you're going away from the reference point, and negative velocity meant that you're going towards. It could happen. But when I go past Wichita and end up in Winfield, okay, I'm still going in the same direction. Just because I go past the reference point does not mean that my velocity vector changes sign. Because what's the only time your velocity vector changes sign?
You change direction.
You change direction. Did I change direction when I went past the reference point? So therefore, my velocity vector didn't change sign. Okay? So this is going to be one important thing. Just because you have a positive or negative velocity, you cannot tell just by that information where you are in terms of the reference point. Okay? I might have negative velocity and going towards the reference point. I might have negative velocity and going away from the reference point. So when you look at positive or negative velocities, the only way that you can figure out if you're going away or towards the reference point is actually figuring out what that position is. Okay? So that's why I said, don't try and form that pattern that, oh, positive means you're going away and negative means you're going towards it. All right, so let's say that our ill-fated trip took 1 hour and I got a negative 100 kilometers per hour. Okay? Okay? So it's still negative 100 because I'm still going in the same direction. Okay. Now at this point, we end up at Winfield at 9 o'clock on a Friday night. And if you've ever been in Winfield at 9 o'clock on a Friday night, you're going, we need to get out of here. Okay. So we're going to go and realize, hey, we got to get to Bubba's anyway because there's a big party going on. So we're going to go from Winfield, America, back to the thriving metropolis of Wichita. Okay? Thriving metropolis of Wichita. So here's the question. On that run, okay, on that run, Matt, what's my initial position?
Negative 100.
Negative 100. All right, like that. What's my final position?
0.
0. So here's the million-dollar question. What then is my displacement?
100.
100. Why?
Because you change direction, so sign changes.
It's true, but mathematically, why is it 100?
Because 0 minus a negative 100 becomes positive 100.
Beautiful, okay? So if you go back to that definition of how you calculate displacement, I'm going to take 0 minus a negative 100, okay? Because that's my final position. That becomes 100 kilometers. And again, this is what you're going to do wrong. You're going to say, oh, negative 100 and 0. My displacement is negative 100. Burkamp, what are you ranting and raving about? That's what you're going to do wrong. It is the little things that make the difference in calculating this displacement. Now, again, that took an hour. Oh, lo and behold, like Hunter said, wow, now my velocity becomes positive 100 kilometers per hour, okay? Because lightning goes from negative to positive. Change direction. Ah, that's kind of cool, right? So if you look at your vectors, so we had this velocity vector coming down here like this, and then, miracle of miracles, we changed direction and we're coming up like this. So in one situation, I had a positive velocity vector that was taking me away from the reference point. But if I'm down here, that positive velocity vector is taking me towards the reference point. But what do these two vectors have in common, regardless of the reference point?
Same direction.
They're both going in the same direction. So that's why I said the sign of your velocity vector tells you which direction that you're going, but it does not tell you where you are in terms of the reference point. Okay? Cool with this? Got it. Okay. Now, let's talk about some different concepts in terms of this whole thing. So one of the things you can talk about for this entire trip is what we call, right, that average velocity. Okay, so your average velocity is P minus P naught over time. Now this is going to get a little bit weird, okay? I'm just going to tell you that right from the get-go. So for the overall trip, for the entire thing, what was my final position? 0. What was my initial position?
0.
0. And that took 8 hours. So overall, what was my average velocity?
0.
0. You're going, oh, no, Mr. Burkamp, come on, this was a good road trip. I mean, we had snacks and M&Ms and, you know, plastic bottles because we haven't got the steel cans yet, okay? And we're, you know. But anyway, so it's like, this was a cool road trip. What do you mean the average velocity was 0? And it's true, in terms of an average velocity. If you think about it, you spent 4 hours with a positive velocity, and you spent 4 hours with a negative velocity. On average, your velocity was 0. Now, I'm not saying you didn't go anywhere. That's not what I'm saying. I'm just saying, on average, if you look at your overall final position and your overall initial position, on average, your velocity is 0. But now, let's talk about speed, okay? So this is how you calculate average velocity. But if you talk about speed, it's something different. So speed is distance divided by time. So for the entire trip, Alec, here's my question. For the entire trip, what was my entire distance traveled for the entire trip? Beautiful. Because I went 300 to Kansas City, 300 back to Wichita, 100 down to Winfield, and another 100 back to Wichita. So my overall trip in terms of distance traveled, so if you're looking at your odometer, right, your odometer would show that you went 800 kilometers. So this one, for the entire trip, my distance traveled is 800 kilometers. That took 8 hours. So my average speed is 100 kilometers per hour. So, but here's the difference, okay? If Garrett comes to me and says, hey, Mr. Burkamp, wow, after school we had a great road trip. We averaged 100 kilometers per hour. Okay, cool. I have no idea where he went. I mean, he could have been in a plane flying to Colorado. I don't know. He could have driven down to Texas, he could have driven to Arkansas, even worse, okay? I don't know where he went, okay? He could have driven around in the parking lot for 8 hours, okay? Should be kind of weird, okay? But if all he says is that I averaged 100 kilometers per hour, great. I don't know where he went. Now, if he says, oh, Mr. Burkham, I drove 100 kilometers per hour west for 8 hours. Oh, okay, right. He's headed towards Colorado. He's headed towards Texas, or if he goes south, or Nebraska, whatever, okay? So, speed is just a number. But as soon as you take that number and give it a direction, then it becomes
Velocity.
a velocity, okay? See the difference between the two. Got it. Okay. Now, here's the next big thing. Now, we're going to spend a lot of time on these. This is what we call a position time graph. Because oddly enough, we keep track of where we are as a function of time. So there's 0 and 1, 2. Okay? So we're going to make Al, being the great physicist that he is, we're going to make him the reference point. Okay? Stay, Al. Stay. Come on, work with me. Okay, there we go. So Al's the reference point. Okay? 0. Do you want the positions going on this side, from your perspective, do you want the positions over here to be positive or negative? Negative. Negative. Why? Because it's like a number line. Okay? So here's Al, right? Big here, Al. And you say you want these positions to be negative.
Yeah.
It's funny because first block, pick those to be positive. So
First block's done.
I don't. That's first block. Yeah. And we got positive 1, positive 2, positive 3. Okay. So do you want me to move to the right or to the left first?
Left.
You're right. This side? This side.
Right.
Okay. All right. So you're going to have to move the camera a little bit.
Okay.
Okay. So we got the timing twins over here, and they happen to have stopwatches. Okay? And so I'm going to start at the reference point. I don't have to start at the reference point, but I'm going to. Okay? I'm going to start at the reference point. So we're going to go click. Okay? I'm going to take a nice leisurely stroll over here. Moved about 3 meters, and that's going to say take about 3 seconds, right? Right? 3 seconds? Cool. Okay. Yeah, pretty close. All right. So here's the drill. So I'm going to come in here and I'm going to say, okay, this, and then we went. Here's 1 second, 2, 3, 4, 5. Okay. So at the end of 3 seconds, I've got this action going. Okay? So, is that enough information to find the slope of that line?
Yes.
Okay? So, I got a data point out here of 3 seconds and 3 meters, and I started at 0, 0. Could I find the slope of the line?
Yes.
Now, what's the slope of the line?
1.
1 meter per second. Oh, because if you just say 1, guess what? What does, I don't know what it means. Okay, 1. What? Squirrel per duck? I don't know. Okay, that's weird, isn't it? But let's look at this, right? Oh, right. I'm going to take delta y over delta x. So that's going to be 3 meters minus 0 meters. Oh, now look. What's my final position?
3.
3 meters. What was my initial position? 0. Oh, guess what I just found on top? Oh, I found displacement. Oh, that's kind of cool, right? So then it took
3 seconds.
3 seconds. Oh, that's kind of cool, right? So divide that by 3 seconds, I get
1 meter.
a velocity of.
1 meter per second.
So what does the slope of a position time graph always give you? Gives you velocity. The slope gives you velocity. So wherever I put my golden rules, golden rule number 2. slope of a position time graph is velocity. Okay? Alright, that's kind of cool. Now, you can memorize this. If you're a memorization kind of person, memorize it. Or if you can just look at the units and go, oh, hey, position is in meters. That's on my y-axis. Time's on my x-axis. Oh, changing y over changing x, I get meters over seconds. Okay? So if you want to do that, you can. Okay? So there's no variation to this theme. There's no exceptions to this rule. As soon as you see a position time graph, you know the slope is going to give you velocity. Okay. Now at this point, so I'm over here, right? And I started at the reference point, and I moved over here 3 meters. So I'm here, right? Came over here. Now, at this point, I'm going to pause for dramatic effect. Okay? So what's that line going to do?
Flatten out.
It's going to do one of three. It's going to do one of two things. One of three things. It's either continue sloping up, it's going to be horizontal, or it's going to slope down.
Horizontal.
Horizontal, right? So how do you show an object that's at rest on a position time graph?
Horizontal line.
Horizontal line. Now, at my age, I don't want you to say flat line. I have bad feelings about that. Okay, as you get older, it's like there's certain words you don't want to hear. Okay, flat line is one of them. Okay, so let's go with a horizontal line. So if I come in here, right, and kind of release this. Okay, that's cool, right? So this is going to be a horizontal line. Now, what's the slope of a horizontal line? Don't make this difficult. 0. Oh, but slope also represents
Velocity.
so guess what?
Velocity 0.
Velocity is 0. Oh, I'm at rest. Oh, okay, cool. So a horizontal line indicates that you are at rest. Cool with that. Okay, so stop that. I've got pretty defined parameters. So what do you think my opinions of cornrow is going to be?
You look like Riff Raff, do it.
Typical truck stop.
I wouldn't say no. Okay, now, that's just me, okay? I know you'll find this probably shocking, but I'm pretty conservative. Except for like the 90s, which I don't remember half of, but that's a whole nother story. No, I'm kidding.
Yeah. My role model.
Yeah,
It's a memory drug.
Okay.
You should own it.
It's like I was in a band, I had groupies. It was
Were you a
weird.
cool kid? Were you a cool kid?
Okay, really? Okay, no, great. Let's put this in perspective, okay? My full name is Stanley Eugene Burkett.
My dad's name is Eugene. What's wrong with that?
No, I'm just saying, in combination, okay? It's like God smiled upon me and said, Stanley Eugene Burkett, this man is destined to teach physics. I could, with that name, I could not be like a starting quarterback in the NFL.
Sure you would.
No, not with that name. No, seriously. Your name defines your role in the NFL. If you have a Polish name, guess what? You can either play linebacker or line. That's it. Okay? No, like your name is like Pulowski. You cannot be a quarterback with that name.
Or fullback.
Or fullback. No, seriously. I mean, if you think you go look at the NFL, your name defines what positions that you can play. Not so much in like the NBA or other sports. Football, your last name defines your role position.
So you should have just played tennis.
Are you saying
But
that
you-
Northern Europeans are typically bigger than? That's almost a Northern European name.
No,
and a linebacker is bigger.
Not necessarily. But, okay, more thicker bone.
Mr. Burkamp, though, you're a big G. You're the rapper Big G.
When I was in the band, I was little G. Yeah.
What position do you play? Yeah, what?
I was-
Are you on Spotify? Do you have a SoundCloud?
I have no rhythm.
He had the fog machine.
I've seen it.
Where was the fog
I can't.
He did look at you got something on your shirt.
Yeah. And you fell for it.
Yeah, I did.
I wasn't lying.
All right. So back to our story. Now, this is going to require some serious, fast action camera work on your standpoint. Okay. Yeah. So here's what we've got. I was here, right? I took a nice, leisure stroll here. I paused for dramatic flare. Now, don't blink, or all you see is just this blur of white. You might not be able to film this. It's going to be that fast. So I'm here. Okay, stretch. Okay, good. So I'm going to run on this direction, okay? Ready? Here we go. Whoa! Zoom. Okay. So, it was just a blur, right?
Flash.
It was
Literally
a blur,
the
right?
Yes.
Thank you,
I didn't
thank
see
you.
a thing.
Okay. Wow. Light speed work camp. That's what they call it. All right. So I went from here at +3 all the way over there to -2 in 1 second. Whoa. Whoa.
I think it was more like
So I
1.3.
went from +3 to -2. Okay.
Just shaking his hand.
What's my displacement?
So 3 to -2.
I went from 3 to -2 in blinding speed.
Is that -5?
-5? Everybody cool with -5? Or is it +5?
-5.
Negative.
-5.
So, the gun show back there. So, what? You started it. Okay? You started it. You're the one that was rolling the cigarette pack up in the sleeve, man. Okay? So, why is it -5?
Because 3 plus -5
It's the It's minus
This is why he works out.
right there.
So, how do you calculate displacement? What minus what? P minus P naught. What's my final position? My initial position is, there you go. So if I take my final position, which is -2 meters, minus 3 meters, now I get -5. Don't add that because you're just going to make it god awful complicated. Okay? Because it's always final minus initial. Don't throw addition into this scene. It's always minus. Okay? So now I get -5. Now that took a blinding 1 second. So here's my velocity. Was it negative the entire time? From there to there, was it negative the entire time?
Yes.
But I went past the reference point.
But you changed
I
direction.
didn't change direction. Okay, I didn't change direction. So therefore, if you consider, we'll talk more about this. This is a slider rule that belonged to one of my uncles, and this is actually what they used to do most of the computation that got us to the moon. Okay, we'll go through how this worked before or later. And so if you consider this like being the vector, okay, so it shows the direction. So I was over here, the vector was pointing in this direction because I was going this way. I stopped, right? Then it's going this way. But even though I went past the reference point, guess what? Beautiful, because it's still pointing in the same direction. Okay? Nice. Okay. Now, at this point, I'm completely out of breath. I gotta stop, right?
Yeah.
Little subtle flat line, okay? Right? So we're here, okay? I'm gonna rest. Then what's gonna happen? Now I'm gonna go back to Al, right? So I'm here, right? I'm gonna go in this direction. So now what? What's this line gonna do?
It's going to go up.
It's gonna go up. Did I change direction here?
Yes.
Yes? How do you know?
Velocity changed signs, so that means direction must change.
Beautiful. And how do you know that the velocity changed signs?
Because the slope is.
Beautiful. Okay? So when the slope changes sign, that's when you're going to change direction. There's no variations to that rule whatsoever. Got it?
Got it.
Good. Fantastic. Okay, we're done for the day.
Max, hit the end record.
Dude, end it.